All right. So keep these two models in mind when we are learning about assumption. You can see I've not put a hat here. I'm not writing beta 1 hat, beta 2 hat, beta 3 hat. I'm writing betas only, and there's no hat on the U also. So we are talking about population regression function, and these assumptions apply to the PRF. All right, now the third one, it says that the mean of the disturbance is zero. It simply means that for a given x, so for a given x, x1, we have many u's, some positive, some negative. This is the mean in the center. You can call it expectation of y given x. So that's the conditional mean of y given x, right? Now, if we talk about the mean of errors and I replace y with u given x, this is the quantity we are talking about, and we are saying that this is zero. It means that all the positive and negative errors cancel each other out, so that the mean of errors, conditional mean of errors for every given x, for this one, for this one, for this one, for this one, they are all zero. The implication is that because we are assuming our PRF to be as close as possible to all this population data, we are in effect saying that PRF passes through the means, and we know that if you take deviation from the mean itself, they will all add up to zero. So in effect, we are saying that sum of errors is zero, so that the mean of errors, which is equal to sum of errors divided by number of errors, is also going to be zero. So keep this in mind. We discussed this assumption also last time. Today we'll talk about assumption 4, which says that there is homoscedasticity, or in other words, there is no heteroscedasticity. So this is our assumption about the PRF, and we can call this assumption to be the assumption about constant variance of the errors. So what does this mean? Again, we are talking about conditional variance. Remember, it's not written anywhere here, so I'm writing it for reference. Conditional variance. We are talking about conditional variance. And conditional variance is constant. That's what our assumption is, right? Now, what does this mean? What is the meaning of variance? Let's start from here. What is variance? We have UI and we have a column of numbers, which we can say is our UI. Of course, we are talking about population, always keep in mind. So this is all the errors that are there in the population, right? So we will not be considering this whole list of errors as one variable. No, because in this case, we will say, okay, it has some finite variance. For example, suppose variance UI is equal to 0.7, right? So of course, it's a constant, it's a number, so it's a constant. For the whole population, there is one number which is variance UI, and it is 0.7. So of course, it's going to be constant. and one number. When we talk about something being constant, and uh, it can be one number, but you can think of this constant being a variable also. So it's a variable, but it doesn't change. That this also means that this variable might change, but in a special situation, it's not changing, so it is constant. In that sense, we are understanding this assumption that we don't take the list of UIs like this. No, we have to write our X here, and we have to write our X values. For example, these are certain X values, and these are certain X values, and these are certain X values, and they are different from each other. For each given value of X, what is the variance of U? For another value of X, what is the variance of U? So we take these lots. For this value of X, what is the variance of U? It will all be same. That's what it means when we say homoscedasticity is present. Right? So this assumption talks about constant variance. It means that for each given value of X, the variance ui given X is constant. And it is, we call this constant to be sigma squared. Sigma squared. So this is the notation that will be used. So whenever you will see a sigma squared, you will think of it as the constant variance, constant conditional variance of the errors. So you will think of it as variance ui given X. Right? Now, if you see a small I here, it means the variance is changing. Variance is not constant. It means that for this given lot, given value of X, the variance of UIs is something, so let us say 0.3, and for another value of X, the variance is say 0.5, and for another value of X, the variance is say 0.9. So it is changing. It's not constant. In that case, you will put a subscript I here. This I says that whenever this I changes, this number changes. So if you don't see a I here, it means the variance is constant. And if you see a small subscript here, it means that the variance is variable, right? So that's homoscedasticity. Now the question is, why do we assume this? Why do we assume our variance to be constant? Any idea? Okay, before coming to this question.
So, we assume it to be constant so that there is no systematic error in the model.
Yeah, yes, you were right, because if it is, in a way, this is right. This is right way of putting things, because we don't want errors to be systematic, so that if X is changing, the error should not change in a systematic way, because if it does, we will have variable variance, right? So there is no change in variability across X's. Let us see this before coming to this question. I'll come back to this question. Let us see these two graphs here. Here, we have homoscedasticity, and here we have heteroscedasticity. So we this is what we want. We are happy here, but we are not happy here. That's bad. So this is good. This is bad, right? So what do we see here is that you can think of the distance between the tails of these distributions to be a measure of variance, which is not exactly true, but we can always have. I mean, it is definitely a measure of variance, no doubt about that. Sort of a measure of range better than variance. Anyways, so you can see these distances between tails is same for all x's, for a small x, for a bigger x, and for the biggest x value. This variability in y, this is y, so that the variability in errors, which are just the distances between each point and the line, and we have a line in the center. This is the regression line. These are errors, positive as well as negative. They have same or constant variance. This is what is desirable. This is what is good. That's what our assumption is all about, homoscedasticity. Now here, you can see that this is a small range or a small variance. It's a bit bigger than that, and it is biggest here, long distance. So a lot of big errors also present here, apart from small errors. So this is a small error, and this is a big error, like positive and negative. So we have big errors and small errors. Here we have small errors and medium errors, and here we have small errors only. So there is a difference in variance. In to be precise, the variance is rising. Variance UI is rising in this graph, and x is also rising. As x is rising, variance is rising, right? As x rises, variance UI rises in this case. So what does it mean? You can take one example. Let us say our dependent variable y. Let me clear this everything from here.
So, what is the meaning of this? Length of the curve in figure B.
This is b, right?
Variance is the spread, then what is the length called?
Which length? This errors, length of error.
No, sir. Like in the first figure, they all are equally high. Like
Hmm.
there is equal highness, if that's a word.
Hmm.
But in
Hmm.
figure B, they're not also equally high. Like one is very high peak. It looks
Hmm.
like a
Hmm.
tall hill.
Okay, so
Then
we will talk about peak also, right? We'll talk about
okay.
peak also. Just let me clear the meaning of homoscedasticity with an example, then I'll come to peak, right? I'll come to peak. So this is homoscedasticity, and this is heteroscedasticity. This is good. This is bad. Let's take one example. Suppose let y is uh, typing errors, number of typing errors, and let x is hours of practice. Or I think this is not good here because errors are rising, so that's not a good example. Let me take another example. Let us take the same consumption income example. So suppose this is consumption and this is income. This is consumption, this is income. So consumption depends on income. If income rises, consumption rises. That's good because you can see this line is going away from the x-axis. This is the x-axis, income axis, and this line is going away from the x-axis. That means as x rises, y rises. Y is rising. When x is rising, y is rising because of this line going away from the x-axis. That's how we draw our graph. If this is the x-axis, this is the y-axis, and the line is going away from the x-axis, it means if x rises, y rises, right? So that's good. If x rises, y rises. That's what this line is telling us. At the same time, people having low income, low x. So we have low income here, low income of 100. And there are people having high income of, say, 500. So those people who are poor, who have low income, they have less variability in their consumption. So their consumption would go as high as this point, and it can be as low as this point, so that the variation in their consumption is very less. But for people who have high income, there can be people out of them who are consuming very less, and there are people who are consuming a great part of their income, so their consumption is very high also. So we have all sorts of people in the bracket of 500 income, those who are consuming a little part of their income, like only 100, and there are some people who are consuming most part of their income, for example 490. But for those who are having an income of 100, they are consuming as low as, say, 70 and as high as 95. So that the variability, which is clearly evident in these numbers, is very less from 70 to 95. That's the variability. But here it is 100 to 490, which is very high. So as income rises, consumption rises, but the variability in consumption also rises, and this variability is nothing which is nothing but the non-constant or increasing variance, right? So we don't want this to happen. What we want is that for people having low income, the variance is same for people having an income of 500, so that the variability is same. That's what is evident in this graph. This is what we want. So we'll come to the question why we need it. But before that, let me answer this question. What is the meaning of the peak? The peak says that if there are 1,000 people having an income of 100, and there are 1,000 people having an income of 500, So when you fit these 1000 people in this range from here to here, of course they will stack over each other and the peak will rise. So the height of the curve for a given value of y tells us that how many people are there who are spending a particular value on consumption. Now you are spreading these 1000 people in a long range so that there are very few people stacked one over each other for any given value of y, so that the peak does not rise that much. So the peak will depend upon how many people are there who are being observed. If there are a lot of people and the range is less, height will be more. If there are a lot of people and the range is also a high number, so there's a lot of range in which you are going to distribute these people, then height of the curve will not rise. Did you get the answer, Priyank?
Uh, no, sir, I did not understand. Could you please again explain again?
Okay, so let me take this graph. So I have just drawn the same curve here, and the bigger one, and I am drawing the smaller one also. So we have this, there are 10 people having a consumption of 70, and there are 12 people who are having a consumption of 75, 12 people, and there are 15 people having a consumption of 80, and there are 12 people having a consumption of 85, and there are 10 people having a consumption of 90. So 10, 12, 15, 12, 10. In this case, now how much this add up to? 10, 12, 15, 12, 10, 59. 59
Yes,
people are
sir.
here.
Yes, sir.
Let me put these 59 people here. So there are some people having a consumption of 80, some people having a consumption of 75, some people having a consumption of 85, some people having a consumption of 70, some people having a consumption of 90. When you distribute the same 59 people here, suppose, and there are only two people having a consumption of 70 and two people having a consumption of 90, of course, there will be more than 12, 15, 12 people who will be consuming 75, 80, and 85. So that the height of the curve, which tells us that how many people are sitting at the consumption of 80, that would be more than 15. It would be, say, 25 or 20, 20, 23 here, and it will be, say, 18 and 18 here. They will all add up to, still they are not adding up to 59, right? That's why we have a high curve when we have less people sitting in the tails. So there will be more people sitting at the center. So the height of the curve will rise. So basically the curve is nothing but the density. so that we have a lot of density in this curve, so that many people are, there are a lot of people having a consumption of 80. Here, it's not that much dense. It's spread across the values more. This is not spread across the values. This is more dense, so that the height of the curve is more in this case, because the height of the curve tells us about density. Did you get it now?
Yes, sir. So basically, the peak of the curve tells us about the probability density of the errors, whereas the variance tells us about how equally the errors are spread. And we want that equal spread because we want randomness in the model and to avoid systematic errors.
So did you understand this? Why do we have the peak? This peak.
Yes, yes, yes. Like I
Okay.
summarized it correctly,
Okay.
right?
Okay. Any other question here?
So just one more thing. For
Yeah.
assumption three, also our agenda was to assume the conditional mean between mu I given xi to be zero, so that we do not have systematic errors. And over here also the similar agenda is there, that we do not want. We want the randomness in errors to be there, right, sir?
Yeah. We want randomness in errors, but at the same time, randomness would not be sufficient. We are going a step higher than that. We are saying that variance is constant, which is different from saying that randomness is there and the mean is zero. So we are adding some information from that assumption, because in that assumption we said that conditional mean is zero. Now we are saying that variance is constant. So we are adding more information here. Of course, you are right that it all begins with this assumption. So what we are adding, that's what I'm going to tell you now. What is the extra information in this assumption which we don't have in the zero mean assumption, right? That extra information is because why do we have a regression model? That's what we have to think about first. Why do we do regression? What is the purpose of regression? One of the main reasons or purposes of regression is prediction, right? And when you are predicting something, you you would be better off if you are aware of the variability. For example, let me take a very simple example to understand this fact. So suppose you have, suppose if income is 100, consumption is say 80 on an average, right? So you are predicting consumption to be 80 when income is 100. Suppose this is your prediction from regression. Of course, we have not studied how to do these predictions, which we will learn. But let us suppose our regression, we have run a regression, and now we are saying on the basis of our regression that if the income is 100 on an average, people consume 80% of that income, right? Now let us consider another. Now, what we have not said here is what is the variability? What is the variability? We are not saying anything on variability in this case when we are predicting this, right? Now, whatever is the variability, say variability is 10, suppose, whatever it is. We have one regression model, one beta 1, one beta 2, say beta 2, beta 1 is 2 and beta 2 is 0.85. On the basis of these betas, we are predicting y to be 100 for a given x, which is y to be 80 for a x, which is 100 on an average, where the variability was 10. Now, if we use the same betas for predicting consumption for an income of 150, and it turns out to be, say, okay, let us take 160, and it turns out to be something like 125, suppose. So that's all an average, right? For all people having an income of 160 would consume 125. And we have predicted this on the basis of beta 1 is 2 and beta 2 is 0.85. Now the question is, what is the variability? If variability is 50 in this case, then we this result, we would not be that much sure here as compared to here, because there is a lot of variability. We can have people who are having a consumption of uh, of say 80 also in this class. In this class of people of income of 160, there can be people having a consumption of 140 also, because there is a lot of variability here. 50 is the variability in this group, right? So we have to take into, while calculating everything, we have to take into account what is the variability. Variability should not be different for different levels of access, right? To be able to predict things correctly, right? So we need our variability to be same if we have to make our predictions better, right? So in two-dimensional graph, if I draw a line here, if this is the variability here and this is the variability here, we can predict this number good, but we cannot predict this number to a good extent, even though mean is zero, because positive and negative cancel each other out, but there's a lot of variability, right? So we need to have same variability across all axes to be able to predict things better, right? So we need to have an assumption of constant variance, right? So that's the additional thing. Apart from mean being zero, we need to have constant variance also. So as
Uh,
we will go further, we will understand it better, because we have one complete unit on violation of assumptions. Violation of assumptions. So in that case, we will study homoscedasticity and heteroscedasticity in great detail, and we will be studying that what happens if the assumption of homoscedasticity is not true. In there we will be studying this in great depth, and you'll be understanding it in better than now.
Sir, I don't know if I got it wrong, but you are basically trying to say that we want the variance to be the conditional variance to be zero, so to be constant, so that we have equal spread of x value, so that we are able to predict the model better.
No, 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 no. We want equal spread of y values for a given x, so that uh, all the variance, all the variability across all the axes is same, so that we can do our regression better and we can make our regression do better in terms of prediction, right?
So, I've written that we want the spread of y values for given x to be constant, so that we are able to predict the model better.
Yes, yes, exactly.
And the third assumption was for the lack of systematic errors, that we do not want systematic errors. The fourth assumption.
Yes, 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 yes.
All right, so thank you so much.
So we don't have time for assumption 5 now. We'll continue tomorrow. Let us stop here. If anyone else has any questions, please ask, because only Priyank is asking all the questions. Anyone else?
So we were writing in chat, some of us sometimes.
Okay, please do not write in chat if you have questions, because I am not able to see them. Okay,
For the
please.
fourth one, still it was somewhat clear, somewhat not in between.
Which part?
Sir, I basically got the meaning that if the variance is constant, it is very good for the good for us, and if it is not, it is not good for us, as we have small errors, and when
Hmm.
we have low variance, the variability between the errors is also small.
Mm,
So this is what I
right.
got. Other part I didn't.
Yes. Yes, you got it right. We need our variance to be constant. So we need homoscedasticity, not heteroscedasticity, because in that case, it will affect our predictability and we will not be able to fit our model better. Our regression would not do a good job. We will study about heteroscedasticity and homoscedasticity in a lot more detail when we come to the unit of violation of assumptions. So up to the definition point of view, in fact, I've told you a little bit more than required at this stage. Uh, Here, it was not required. Here, what you need to understand is what is the assumption, what does it mean, right?
Okay, sir.
Not
So
we. I don't want you to understand that much. Why do we need it? I just wanted to give you a hint, and that's it, right? So please don't worry. Just have a reading of assumptions, and we will study it in a lot more detail later, right?
yes, sir. So in the next class, can you please repeat the assumptions for once? Like, uh,
Okay, I'll do that definitely because I always repeat what we have done in the past classes when I start a new class. So I'll be repeating the assumptions once more quickly before coming to assumption 5.
thank you, sir.
Yeah. Okay. Who is absent, Priyank? Can you just have a look at the
Yes, sir.
list of.
Sir, only Stuti is absent. I'll send you her name over text as well.
Okay, okay, okay.
Thank you, sir.
All right then. So we stop here. Thank you.
Thank
Have
you,
a nice
sir.
day.